Here we have a ramp, an inclined plane, that can be used for moving things into a truck. The ramp is 2 meters high. It's at an angle of 20 degrees, and we have a 400 Newton box that you're going to be pushing up the ramp here. Now we're going to find the IMA. The equation for IMA is the distance input over the distance output. The distance output here is basically will be the 2 meters of height that you're going to gain. What's a little bit more difficult here is the distance input, but really what it is in this case is the length of the ramp, the hypotenuse. We're just going to call that L. This distance right here, call that L. How far you're pushing, that's your input distance. Your output distance, we already know, is 2.0 meters. But what's your input distance? We'll just use the sine. The sine of 20 degrees is 2 meters over L. Solve for L. L comes out to be 5.8 meters. Let's kind of circle that. But it goes over here on the right, 5.8. So your IMA here will be 2.9. So that's our answer to part A. So if we rounded that off to 3, that means you'll be pushing 3 times further, but you'll be using 1/3 the force to lift the thing directly. All right, part B here is pretty simple in this case because it says there's no friction. Whenever there's no friction, it's automatic. E is 100%. Now, let's factor in friction though. Question number 3 below, I'll start it here, but it says there's a coefficient of friction of 0.3. What we'll need to do now is, like we've done earlier, is draw the free body diagram for the box. Now, let me set this up. I know there's going to be a weight vector straight down of 400 newtons, so this will look familiar. This is what we did when we did the ramp problems with Newton's 3 laws. So we draw the weight vector straight down 400 newtons, and we have W sub n and W sub p, and the angle here is 20 degrees. Let me see if I can squeeze that in. 20 degrees. And if you use sines and cosines here, and I'm going to skip that step, which you are allowed to do, but drawing a diagram is good there. I would like you to do that. But just tell me what it, get your calculator out, solve for W sub n. You'll be using cosine for that. W sub n comes out 380 newtons. And W sub p comes out to be 140 newtons. Those are important numbers for our free body diagram. So let's go to the free body diagram. And let me draw that. So here's the box, 400 newtons. But I have W sub n, which is 380 newtons. I have F sub n, the normal force, and I have W sub p, which is 140. If you think back a couple weeks ago, every ramp problem starts this way. You have your 2 components for your weight vector and your normal force, which is always equal to your weight vector. So F sub n here will be 380 newtons. But what else do we have here? Well, we're going to be pushing this box up the ramp. I'm going to call that the force of push. And we're not going to accelerate the box. We're just going to push it up at constant velocity. But as we're pushing with constant velocity, there will be a force of friction working against. All right, so now I have this set up. And let me switch to the next screen here. All right, I've redrawn the diagram, and we need to find the AMA. The formula for AMA is your output force divided by your input force. The output force is the weight you're trying to lift. In this case, it was a 400 Newton box, but you're not using 400 newtons to lift it because you're using a simple machine. It typically lessens your force. But what is the force you're using in this case? It's the force of your push. Using Newton's second law, F net equals ma, we know F net is 0. and therefore along the direction of the ramp, the force of the push must equal W sub P plus force of friction, because those are the two forces that are down the ramp. So the force of the push will be the 140, I already have that labeled, plus the force of friction. Let me do that off to the side. Force of friction is the coefficient times the normal force. The coefficient here is 0.30. The normal force is 380. It's equal to the weight perpendicular, the normal weight. Force of friction comes out to be 110 newtons. So I'm going to bring that over here and calculate the force that it's required to push the box up the ramp. It's 250 newtons. So that's our input force. So that goes over here to calculate our AMA. So it's 400 divided by 250 to get the AMA. The AMA therefore is 1.6. The actual mechanical advantage. Now we have to get to the efficiency because it's not 100% in this case. We got to go back to the previous problem to finish this off, but the efficiency, we're just going to use the AMA over the IMA. Since we have both those values, the AMA is 1.6, the IMA was 2.9, so the efficiency comes out to be, in decimal form, 0.55. That is 55%. And that, my friends, is how it's done. One way to summarize the work done by a simple machine is like this. W stands for work, and work is force dot distance. Let's just say we're going to ignore the dot product right now, the cosine of the angle, but the work can be done several different ways. You can, in case number one here, at the top, you can use a moderate force times a moderate distance to do the work. What the simple machine does, either the lever, the pulley, or the inclined plane, allows you to use, say, a small force over a big distance to do the same amount of work. Because once again, you still have to do the work. The machine is not going to do the work for you. It just manipulates the size of the force that you're using to do the work. So if you push an object up a long, long ramp, you have a long distance with a small force, as opposed to if you had to lift something straight up onto a truck or something, you would use this last equation, a large force over a small distance. You might be able to get the job done a little faster, but you're still doing the same amount of work. In fact, when you're using levers, pulleys, and inclined planes, most likely there'll be friction involved, and if you're using a ramp or a lever where there's a small force and a long distance, it's likely you actually end up doing a little bit extra work if there's friction. So that's the theory of levers, pulleys, inclined planes, simple machines. They do not do the work. You still need to do the work yourself. Sorry, folks.